Okay, I'm hoping to give a little bit more understanding on when we are dealing with a compression or a stretch on a rational function. Remember, the parent function for the rational function is y equals 1 over x. You will sometimes hear it called a reciprocal function because it's like y equals x flipped over to be 1 over x. I've got the parent function here in a dotted line. And the first thing that we will look at is when x is between 0 and 1. So that's why you see I have these functions here with a fraction. So for example, if it was 1/2, 1 over x. If I zoom in, you can see the blue line is actually coming closer to the origin point of 0, 0. So out here, like the further out you go, you can see the blue line and the dotted line almost look the same, but right here in the middle of the graph is where you see more of a difference. It looks almost, if you imagine taking the dotted line and putting, if you put one hand right here and one hand right here and squeeze them together, you could push them towards each other to get the blue line. If I add another one here, 1/5 is green. Notice it's even closer to the origin. Basically what's happening is if you think about your graph, in the parent function, y equals 0 and x equals 0 are your asymptotes. So you can't actually cross over either axis, right? Because those are asymptotes. So what's happening when we're vertically compressing it is that the line is getting closer and closer to the asymptotes in the center, because it's basically as if the graph is being squished together. And if you think about it, if you plugged in values for x, it might make sense, because if you think about 1 over x, then that would be when x is 1, that's 1 over 1. So we get the 0.11. But when you have half of that, or 1 over 2x, then when you have x equals 1, y would be 1/2. If x equals 5, y would be 1/5. And you can see here is another one, 1/12. It's getting closer and closer. You can see as we go to 1/100, look how close we are. That red line is very close to the asymptotes, and you can see the original parent function is this black dotted line. As the value of our multiplier, in this case, is getting smaller. If you think about it, 1/2 is bigger than 1/5, that's bigger than 1/12, it's bigger than 1/100. It's actually getting smaller as the denominator gets bigger, the total value is getting smaller. This is getting closer and closer to the asymptote, okay? So that's what we're calling it, a compression. Again, if you imagine putting your hands on the dotted lines and squeezing them towards each other, then you would be compressing it. You're squeezing it into the middle. You're compressing it. So the smaller the value is, that's the multiplier, this value that we could call A, for example, 1 over 100, 1 over 12. These are our multipliers, and they are getting smaller, and so it's squeezing it together. Okay, let's take a moment and look at the opposite. Let me turn these off. And now I'll zoom out a bit. Let's try this one here. 2 over x would be the same thing as multiplying 2 times 1 over x. And I'm sorry, the construction just kicked in. Hopefully you can still hear me fine. So here, notice that our dotted line, to go to the green, it actually moved away from the asymptote. Remember, our asymptotes are the axes, the x and y. Because what happened? Well, whenever we had x equals 1, the original point was 1, 1. What's it going to be now? When x equals 1, we're going to have 2. So the point would be 1, 2. So that's over 1 up 2. If it were negative, it would be over 1 down 2. It would be negative 2, right? So this time, the green line is getting further away. And I'm sorry, I just realized I was pointing at the dotted line when I should have been pointing at the green line. So I apologize for that. So when I said, if you're at when x equals 1, y is 2, that's up here, right? When x equals -1, y is -2, that's down here, okay? Remember, notice that our coordinate plane here is counting by 2's. So anyway, let's look at another one. If we have a 5x, look, we're getting even further away from the asymptote. It's basically that the curve is less prominent. It's taking a more shallow dip. Look at 12. The black line, let me change that color so we can get something different that shows up better. So this line, notice the bigger the number gets, the further we're getting away from our asymptote. Now, as we zoom out, you can see out here, they all look the same. You can't differentiate the color. But as you zoom in to get closer to the asymptote, you can see what's happening is that the curve is just getting more or less prominent depending on the value that we're multiplying by. Okay, so that's what it means by a vertical or horizontal compression. So for example, in the compression, we talked about if you were squeezing the dotted line towards the center, you're compressing it. In this case, imagine if the dotted line is being stretched outward. One way you could think about it is if this dotted line was a string and I put my fingers up here, say at 15, and I pulled the string up, I would get these curves, these colored ones, because the more I pulled the string up, the less I would get the curve. It would get less and less shallow, right? And that's how we would get out here to the red. That's why it's called a stretch. Imagine if you grabbed the dotted lines like here at 15 and way down here at the bottom, and you pulled them away from each other. The two lines would be separating and getting less and less curvature. So hopefully that helps. You can go ahead and play around with the examples on the homework. Let me look at one of those with you. This is number 6 on the graphing assignment, graphing functions. First, I only have our parent function here in a black dotted line. Let me reflect it because in our problem number 6, it's reflected. So the green is when all we've done is reflect. It was a positive 1 over x and it became a negative 1 over x. It looks like you could say it was reflected over the y-axis or the x-axis. We've just made it a negative. Now look what happens when I add 3, because the actual problem that we're going for is negative 4 over x plus 3, but let's just take it one step at a time. So right now we've added the negative. We've taken the parent function and we've put the negative on it, so that reflected it. Then if we add the 3, notice what happens. Look at the green one. From the green to the purple, we shifted over 3 spaces, and that's true on the top and the bottom. Both curves shifted to the left 3 spaces, okay? And then finally, let's put in our vertical stretch. That's going to be the times 4. Notice what happened. This purple line was dipping down pretty good, and now it has less of a curvature. It's coming less shallow. Or more shallow. It's more shallow because it's not quite as deep of a curve. Okay, so as you zoom out, you can see it's hard to tell. It doesn't really look that different because it's going towards an asymptote. But when we're close to the middle where the asymptotes are, this is where we're going to have the more obvious statement of what's happening. Notice when we moved 3 over to the left, we got a new asymptote at y equals negative 3. So this is our asymptote, and then of course y equals 0 is still the asymptote. And I just realized I said y equals negative 3. This is x equals negative 3. I'm trying to talk about too many things at the same time. The other one on the homework is number 8. Again, here I've got the parent function with the dotted lines. If we take it one step at a time, number 8 is 1 over 2x minus 1. So I could do 1 over 2x, and you'll notice that is my compression. It's just squeezed in, coming a little bit closer to the center, which is 0, 0. The minus 1 is actually going to shift our vertical asymptote. I'm sorry, our horizontal asymptote. We're shifting down. We still have an asymptote at x equals 0. That's our vertical asymptote. But it's going to shift down. Instead of being based around y equals 0, it's going to come down to y equals negative 1. So that purple graph, pay attention to the purple one, it's going to shift to where it's aligned around the 2 orange lines instead of the axes. So look at that red one. The red one and the purple one are exactly the same, but the red one is shifted down just 1 space, 1 unit down. Okay, it might look like it's 2 because we're zoomed in pretty tight, and so the graph is showing the, like here right now we zoomed in further, we've got 5 spaces between 0 and 1, but you still have to pay attention to how they're labeled. So when I zoom out, notice what happens. The graph is just shifted down 1. The vertical compression is what makes the curve, the purple one compared to the black one. That's what makes that curve squeeze in a little bit more to the center. So if we remove some of these colors, The red one is showing the shift. The purple one is showing the compression, how the purple is closer together. If you look at these two purple lines, it's as if you squeeze the black ones towards each other. Okay, hopefully that helps a little bit with the vertical compression and stretching.